Welcome to the webinar titled Fundamentals of Reactor Design, hosted by Chemical Engineering Life. Well, my name is Humzaa Imtiaz, and I will be the host for the day. So the agenda for the webinar is that we will start off by looking at some of the basics of reactor design, of course, and then we'll jump into the basics of chemical reaction engineering, which makes up the heart of reactor design, of course. And then we'll look at some of the reactor types and their design equations. And then we'll follow up into the key factors of reactor design, and then concluding the webinar with the general procedure for design, summarizing everything that we will look at in the webinar today. But before we begin, a little bit about myself. Well, my name is Humzaa Imtiaz. I am a chemical engineer myself, having graduated with both my bachelor's and master's from the Technical University of Denmark and specializing in process engineering. I graduated back in 2020, and then since then I have been working in the pharmaceutical sector within the quality area. I also happen to be the founder of Chemical Engineering Life, which I have been since 2021. And Chemical Engineering Life, if you don't know it already, it is an online platform that has been created to connect and help different chemical engineers from around the globe. You as a chemical engineer, or if you are not a chemical engineer, but as an engineer, you can also become a member of the organization. And we currently have more than 500 members all over the globe. And we offer multiple different initiatives to all those members. Some of the initiatives that we currently have is that we have a podcast called Decoding Chemical Engineering, in which we have invited different chemical engineers from different areas and different sectors, and we talk to them about what it is that they're doing with their engineering degree and how it is to work as an engineer in the real world. At the same time, we have different webinars and different courses, which are both online, in which we have different guest speakers and different instructors coming down and giving a lecture on chemical engineering topics and or other topics such as project management, Excel, Python, and you name it. At the same time, the initiative that we are very proud of, that is our free biannual mentorship program, in which we have had so far more than 400 participants in the past 3 years, in which we allow different mentees, which are students and young graduates, and we help them connect with the industrial engineers so that they can ask the right questions to the right people and get the right answers for their future. So if you're not done so already, then do visit our website at www.ChemEnggLife.com, where you can then have a look at some of our initiatives, and you can also sign up and become a free member so that you're notified whenever we go live with a new webinar or a new course, or whenever we have these milestones for the mentorship program. Great. But then moving down to the webinar. So we'll start off by looking at some of the basics, of course. And the very first basic question is that what exactly is a reactor? Now, a reactor is the heart of a chemical process, or whenever you are designing a process, the reactor finds itself in the middle of it. And a reactor essentially is a unit operation where you have a feed coming in. So let's say that you have reactants A and reactant B. They are pushed into the reactor. A chemical reaction takes place within the reactor, and you end up getting a product feed that's coming out from the other side. Now, the product feed, if you are assuming 100% conversion, then you would only have your products coming out. But in the real world, since not everything is converted into your product, so you will have a stream that includes both your reactants and your products. But essentially, in very simple words, a reactor is the unit operation that converts your reactants to your products, and hence creates the basic production of your process design. As you'll see in this diagram right here, in the PFD right here, so you have the entire you have the entire process design, and the reactor itself finds itself right in the middle of it. So all the unit operations that you have before a reactor, then they are placed to prepare the reactant or prepare the feed before going into the reactor. That could be cleaning up the feeds, or heating up the feeds, or increasing the pressure, or so on and so on, so that the conditions of the feeds that are coming in should match exactly those of the reactor. Then all the unit operations that you will see out on the other side of the reactor in the product side, then they are specifically added in order for you to clean up the product feed. So you would like to separate your product to make it more purified from the reactants. And at the same time, if you have multiple byproducts, then you would also like to separate and purify the byproduct stream so that you get a very purified and clean product and the byproduct. So, but we're not going to look at in any of the other unit operations, but we will start looking at the reactor for this webinar. And the reactor is actually a very, even though you have a lot of unit operations in a PFD, a reactor is the one that you spend the most time on, because it has to be designed specifically for your needs and for very specific requirements. At the same time, a reactor is kind of, you can't interchange a reactor. So if you design a reactor for methanol, you can't use the exact same reactor for biodiesel production. So therefore, when you are designing reactors, it's very important that you have all the necessary information, and because it needs to fit in, because it really needs to fit the entire process design as it should, which I will actually look at in this webinar today in the later slides. So at the bottom of it all, there are 3 specific types of reactors. So there's something called a batch reactor, which is the most simplest of all reactors. Then you have a continuous stirred reactor. Then you have a plug flow reactor. Now, for the purpose of this webinar, we are only going to be specifically looking at these 3 basic ideal reactors. You can also have a lot of real reactors, but more on that in later. So essentially, these 3 reactors, they can be divided up into 2 different types of operations. So you have a batch operation, and then you have a continuous operation. Think of the batch reactor as if you're making tea, for example, right? So you take all of your ingredients, you take the tea bag, you take water, you take, I don't know, sugar, you put them into the pot, and then you heat up the pot and you let it be for 5, 10, 20 minutes. And after 10 minutes, the tea is ready, you take it out and you empty the pan. That is very similar to how you do a batch operation. Or that's what a batch reactor is. Your pot, that is your batch reactor. All of the stuff that you're putting in, like the tea bag or the sugar, water, all that is your reactants or your feed. And then the water, and then you're heating it up, and that's your heat operation or the heat transfer. And then you let it be for a specific amount of time, and then your products are created. On the other hand, then you have something called a continuous operation, in which the feed are continuously coming in and the product is continuously leaving the system. And an example of that could actually be if you have a juicer, for example. So you put carrots on one end and the juice starts coming out from the other end. Now you don't necessarily stop putting carrots in, right? So you put one carrot and the juice comes out right away. That's how you can think of a continuous operation or a continuous stirred reactor. A CSTR is kind of similar to a batch reactor, in which you have, of course, a tank, and then you have feed coming in, then you're mixing everything, and your products are going out. And then there are a great deal of assumptions, which we'll also look at in the later stage. But then, similar to the continuous stirred reactor, we have something called a plug flow reactor, PFR for short. Now, the PFR and continuous stirred reactor, they're both continuous reactors, but the main difference being that a PFR is designed as if you're having a reaction in a long cylindrical pipe, whereas a continuous stirred reactor is something that is happening inside a basic tank or a reactor. So like I said earlier, these 3, they are what we call in ideal reactors, but then at the same time, you actually have a great deal of real reactors. Because as we'll look at later on in the slides, that when you are working with ideal reactors, you have to make a great deal of assumptions when you're designing them, when you're deriving the design equations and everything. But at the same time, you can actually have a great deal of real reactors in which you start incorporating a great deal of other information and a lot of other variables. For example, instead of just assuming that everything is isothermal, you can start calculating the heat transfer that you possibly have inside the reactor, just like a fixed fired heater reactor. At the same time, if you have solids inside your reactor and not just gas or liquid, then you can of course have a different type of reactor and so on. But for the purpose of this webinar, we are only going to be looking at the ideal reactors and how to design them and how to work with them. Anyway, but before we start jumping into that, it will be a good idea for us to have a look at the basics of chemical reaction engineering. And just a heads up, I'm not going to go in that much detail in terms of chemical reaction engineering, because that's a topic of its own. And I would assume that you already may have a little bit of an experience or a little bit of know-how about the kinetics and the transfer. So we'll just very quickly and briefly go through it so that you have, I'll just update your knowledge before we start deriving the equations for the designing of the heat reactors. So the very first thing, the basic thing of chemical reaction engineering, that's the rate law. And you all may already be aware that whenever you have a chemical reaction, so you have reactants, they react, and you end up getting a product. So you have A plus B, that's C. That's cool. So your A and B, those are your reactants, and the C, that is your product. But then at the same time, you may remember from chemistry classes that you have to balance you need to balance the chemical reactions, right? So there's the small a, b, and c, those are the stoichiometric coefficients. Now, whenever you're working with the rate law, then you can rewrite all of this in terms of the equation below. So if you write a rate law in terms of A, then you can write R subscript A is equal to K times Ca Cb. And the C, those are the concentration of your reactants. And that is something that we will use later on when we are designing or when we are derivating the design equation for the reactors. There. And then at the same time, we will have a look at the mole balance. The mole balance is essentially the mass balance or the mass transfer area that you already may be aware. So imagine that you have a system in which you have a feed coming in, a mole balance, a mole flow coming in, and a mole flow going out. So the mantra of chemical engineers, or the mole balance equation, that is in minus out plus generation is equal to accumulation. You already may be aware of this equation, the very basic, the most used balance in chemical engineering. And then we start putting terms in it. So you have your Fj0, that is your inlet mole balance. Fj, that's the one that's going out. And the Gj, that is the generation factor. And then the accumulation factor, which is the differential. Now imagine that this gray area that you're looking at, that is basically a reactor, the system or in which you have stuff coming in and going out. Then the most important, and then the inlet and the outlet stream, they are relatively very simple, right? Because that's just the feed coming in and the feed going out. But there isn't really much to say about that other than that you'll end up getting a value and that's it. The same goes for the accumulation. Accumulation is just something that is being accumulating within the system, right? But then we have a very interesting way of defining the generation factor, because there are two scenarios when you're working with a generation factor. You could have a scenario where the temperature and the pressure and the conditions throughout the system, they are the same. If they are the same, or if they are uniform throughout the system volume, then you can write the generation factor as the one on the screen right now. For the generation factor is equal to the rate expression or the rate law multiplied by the volume, right? It actually makes sense, right? Because if the volume is constant throughout, if you're saying that the uniform and the temperature and the conditions throughout the system volume, they are constant, that means that in point A or in point B or point C or point D, it doesn't matter, because they all have the exact same amount of production, or the rate of reaction is the same throughout. Then the generation will, of course, be the rate expression multiplied by the volume. And you will end up getting the total amount of the product that is being generated inside a system. But in the other scenario, as you can see on the screen on the left, if the system is not constant, then it could be that the rate of reaction is faster in one area in V1, whereas it is a bit less in V2, and it could be slightly more again in V3. Then essentially you can write up the generation factor as the sum of all the smaller chunks of the volumes multiplied by the rate of that volume. In other terms, we can write that as an integral, which states that G generation is equal to the integral for the entire V. That means that from different V areas, and then we integrate in terms of V for the rate expression. And that's the expression that we end up getting. So if you go back to the mole balance and we were to put that integral into the balance instead of G, then we end up getting that expression. So you have the inlet minus the outlet plus the integral for the generation factor, assuming we have derived it saying that the volume is not constant, or the rate, the rate of reaction is not constant across the volume, but rather because there are different temperature, different pressures, and so on, so it could be different. And then equal to the accumulation factor. The accumulation factor is relatively simple enough because we are just saying that something that is the number of moles that are being accumulated over a period of time. And that's what the differential then means. So that this mole balance, this equation is the basic equation that we will be using for designing all of our batch design equations for our reactors, which we'll see in a minute. So that's all for the basics to chemical reaction engineering. We will not be looking at the heat transfer heat balance for this webinar, because we will be assuming that all of our reactors are isothermal and that there will be no heat loss or heat gain throughout the reaction. So therefore, we will be skipping that part for this webinar, because this webinar is basically just a presentation for the basics of reactor design and not that much in detail. So, but then we will now jump into the actual reaction types, and we will start off with the most simple one, the batch reactor. And just like I said earlier, so the batch reactor is the reactor that we use for batch operations. Now, I will reuse the same example that I gave earlier. So imagine that you're making tea. You have a pan, you put it on the stove, you put water, you put tea bags, you put sugar, and you let it be for 10-20 minutes, and then you end up getting tea. That's essentially what the batch operation is. You have a tank. It is a non-continuous reaction in which it is conducted where the reactants and the products and the solvents, they do not flow in or out of the vessel during the reaction until the target reaction conversion is achieved. So it could be 5 hours, it could be 10 hours, 15 hours. You let them react within the reactor, and then you just forget about it. And then you come back and you open it, and then you can flow everything out. And many of these batch processes, they are actually used quite often in the industry. Essentially, like for example, like a fermenter, for example, a fermentation, that is a batch operation. Many of you'll see that in the pharmaceutical sector, they use batch operations. In R&D, you have batch operations. And also, if you're doing a very small scale production, then it doesn't really make sense to have continuous operation, but then batch operations are always better. And also at the same time, if you're working in an environment where you have to create multiple products, and you can't really, for example, it could be that you need to produce product A, B, or C, then you can also use a batch reactor. Like, for example, you can use the same pan to make tea, coffee, spaghetti, everything, right? And the same applies to the batch reactor. So if you have a smaller company and then you don't really want to spend too much time or money designing a specific continuous reactor for different products, then you can actually use a batch reactor in that scenario as well. At the same time, it also goes the other way around. So if you have a very high value products, such as in the pharmaceutical sector, then once again, the batch reactors are used a lot more often than continuous operations. And also because every time you have a recipe, and in chemical terms, if you're scaling up something from a recipe, from a chemist's point of view, then also batch reactors are mostly preferred by chemical engineers. But then there are a great deal of pros and cons when you're using batch reactor. So the biggest pro is that it's very flexible in terms of production scheduling. It's because you can easily change the batch sizes when you are, producing something. Like all of a sudden today you need only 10 liters of your product. That's good enough. Tomorrow you need 20. As long as it can be facilitated by the reactor volume, it's very doable. You can easily, you can plan your production and so on. At the same time, you can also, like I said earlier, if you have multiple products that needs to be created, you can do so by using the same batch reactor, using the same equipment, and this versatility actually allows you to utilize the resources and the equipment that you have in hand in different scenarios and for different products. At the same time, the batch process actually requires a lot more simpler process instrumentation. For example, in terms of continuous operation, you don't really need to take care of how fast stuff is coming in and how fast the stuff is going out. You only need to take care of the discrete variables in the batch operation. So for example, it could be that you might end up getting more or less process variables, but they're easier to control and manipulate and measure in terms of a continuous operation. At the same time, the process intensification is also a great pro for the batch operations, because it allows you to, in a batch cycle, you can always facilitate higher concentrations, temperature, load pressure, in order for you to have improved reaction kinetics and higher yields. Not really something, and of course you can, and this, it may not be something that you can say are better than a continuous, but it's slightly more easier to do and easier to model in comparison to if you were doing it in a continuous operation. And at the same time, in the research and development scenario, batch reactors are, of course, used much more than continuous reactors. It's because it allows you to explore the reactions, optimize the process parameters, and you can easily scale up to the production level as well. But having said that, then there are a great deal of cons as well for the batch operation. The first one being that there is a limitation on how much scale up you can actually do. You can't have a batch reactor that is, I don't know, like for example, 500,000 liters, right? So therefore, the scalability is somewhat limited in comparison to continuous processes. And also because if you think of the batch reaction as that it needs, let's say, 5 hours for you to perform a reaction, then you can only use it once, 5 hours for 10,000 liters, then you can only do 10,000 liters after 5 hours. The same problem is not present when you're working with continuous operations. At the same time, when you're working with batch operation, there's actually a higher labor cost involved, essentially because you firstly have to imagine that you have a batch reactor, then you need someone to fill it up, then you need someone to empty it, then you need someone to clean it, then you need someone to also monitor the process conditions at the same time. And so therefore, you actually end up getting you need a lot more hands on deck when you're working with a batch operation. And at the same time, the process variability is also is kind of a mix in batch operations, because when you're working with a batch operation, so let's say that you make tea one day and it tastes very good. On the second day, let's say you try to make it again, even though you use the exact same process, the same, it does not guarantee that you can make it exactly the way you did yesterday. The same applies to batch operations in the industrial scale. Even though you can do everything correctly, everything the same as before, but sometimes, the batches are not necessarily the same, which means that you need to have very, very strong process control and monitoring to ensure that you have consistent product quality. And which again kind of links back to our previous point that it has a much higher labor cost. And also, like engineers that are working with batch operations, then they always have to be hands on deck and always be able to look for any tiny variation that may happen compared to the older batches. And then like I said earlier, actually, like the batch operations, you have a much longer cycle times. You could have, for example, fermentation reactions. They take, let's say, I don't know, 20, 25 hours. And then now you have a reaction running for 25 hours. Then you need to then you need to empty the batch reactor. Then you need to clean it. Then you need to, refill it. Then you need to heat it up from beginning. And then you need to let it run again for 25 hours. So you see, so there are very long cycles that you have to run for batch operations. You don't have the same problem in continuous operations, because in continuous operation, it's continuous, right? So it's just coming in and going out all the same time. At the same time, the equipment utilization, there could be a great deal of downtime between the batches, which kind of I just said earlier, that if you're all of a sudden cleaning your batch reactor, or you are all of a sudden now emptying it, or you are now cooling it down, so there are a great deal of resources that you're kind of missing out on. So that means that in a continuous operation, you could have maybe use those hours to produce a little bit of product, but now you can't do so in the batch because your batch reactor is out of order. So these are like the basic limitations of a batch reactor. Now coming down to the assumptions of the batch reactor. So when you are designing the ideal batch reactor, there are a great deal of assumptions that you have to do. The first assumption being that we assume that there is constant density throughout the reactor. So that means that all the reactants, all the products that are being put in, the density is exactly the same. And the reason we do it is because assuming constant density kind of makes the mass transfer and the volume change calculations a lot simpler. If you were to assume that the density is not the same, then you would have to take into consideration the volume change and the mass change and all that stuff. At the same time, we assume that everything is perfectly mixed inside a batch reactor. That means that the temperature, the pressure, the reaction rate is constant throughout, and that links back to what I said earlier for the generation factor, and that's exactly why we assume it, because then the analysis of kinetics, heat transfer, and mass transfer becomes a lot simpler. Then we also assume that the reactor is isothermal, because it really simplifies the heat transfer calculations for us. And now you're assuming that there is no heat that is being lost or being added. Then we assume that there's negligible change in volume in the reactor. And that links back to the very first assumption that I made, because it allows you to make it kind of oversimplifies the equipment sizing and the volume calculations. And we will also assume for today's webinar that there is no byproduct. So we are assuming that you have 100% conversion, and at the same time, there is no byproducts. So if you wanted to get you wanted to get methanol, you're only getting methanol. You're not getting any other side product. And then obviously we will assume the ideal gas behavior. If you're, that kind of comes in handy when you're working with gas phase reactions or pressure changes, and once again, the volume change. And then once again, we will use the assumption that there is a constant reaction rate because of the generation factor, which I mentioned earlier, and specifically only for the generation factor, actually. And then also, this is not kind of an assumption that we will use for today, but it's an assumption that is used in the industry. That let's say you have 5 batches, or you have 5 batch reactors running parallelly. You will always assume that they're consistent. That the consistency of the reaction behavior and the product quality will always be the same. You can even do so when you're calculating it, and that kind of ends up coming up in the optimization stages, because then you can always assume that all the reactions that you have done, all the equations, all the conditions, they will work exactly as they do, and then you can always use that assumption. Anyhow, but then we will come to the interesting part, and we will have a look at how you can design a batch reactor now. So we will start off with the mole balance, which we looked at earlier. So in minus out plus generation is equal to accumulation. And then if you remember from earlier, so this is the mass balance that we end up getting. Oh, sorry, the mole balance that we end up getting when we put in the variables. So you have the F, and the capital F, it stands for the mole flow. That means moles over time. The capital N, that is the number of moles. Small t, well, that's time. R, that is the rate expression, and V, that's the volume, in case you didn't know that. So we know that inside a batch reactor, there is nothing that is coming in, and there is nothing that is going out. So that means that our first 2 terms, they will then be 0. So Fj0 and Fj, they're both 0 because you have no inflow and you have no outflow. And then now, since we assumed that there is uniform mixing, that means that the temperature is constant throughout the volume, the pressure is the same, hence there's a constant reaction rate. That means that we can then rewrite the generation factor into Rj times V, because now we know that since the volume is constant, so the reaction rate is constant throughout, so the mole balance for the batch reactor ends up looking something like the one on the screen right now. So you have the generation factor is equal to the accumulation factor. There, and then when we end up getting that expression, so what we would like to get out of this reaction is the amount of time it will take for the reaction to take place. Because in a batch reactor, the design variable that we will be using, that is basically time. So how much time will it take for me to react, for my reactants to react together, for me to get the enough amount of product, right? That's the design expression that we're working with for a batch reactor. The volume can be anything, right? You can have, if you have a batch reactor, if you end up getting an expression that time is, it takes 5 hours for A, B to get C, it doesn't matter if your batch reactor is 500 liters or 5,000 liters, it will still take that T amount of time. So that's why we will now solve for T. So if we rearrange this expression, you will get something that looks like this. So now we are saying that the expression for T, dt, is equal to the change in the number of moles divided by the rate times by the volume. And then we will take the integral for the starting amount of moles till the last or the end amount of moles. And then your impression ends up being the one that you see on the screen. Now, what this integral is telling you right now, or what this essentially means, is that you are integrating the term 1 over Rj times B from the starting amount of your reactant till the last amount of your reactant. Or you could start from the starting amount of your products till the last amount of your products. So let's say, and I'll show that, and we'll take the example right now for the first order reaction. So imagine that you have a reaction that looks something like this, a very simple reaction. It's like you have the product A and it converts to product B. The rate expression will then look something like this. And then the Ra, which is our reactant, that would be a negative K, K is the rate constant, times by Ca. Ca because that's the only reactant that we have. Negative because the rate is negative because the reactant is being used up. That means that the reactant volume is, concentration is going down, right? So that's where the negative comes in. Now, many times there are many different, what do you say, the notations that are being used in different books. Sometimes some people, they use capital C with a subscript. That's also okay. Sometimes they use these square brackets, which also means concentration. Either way, they're basically the same. I just wanted to show that you can use two different notations. But then you may know that concentration is equal to moles over volume. And the reason I converted that into moles is because if you go back to the design equation right there, you'll see that we are integrating with respect to moles. So we are not integrating with respect to the concentration, but for the moles. In reality, we could also have converted this into the concentration, but I decided to use moles instead because we're working with the mole flow anyway. So we'll come back. So I convert the concentration to moles. So we say concentration is equal to the number of moles of A divided by the volume. And then we go back to the integral that we had. Then you just put in the number, the expression that we have now written down. And you'll see that the V's, they cancel out. The volume, they cancel out. And, the volumes, they cancel out. And you end up getting an expression that looks like this. And then if I was to integrate, I'm not going to do it now because it's a basic integration. But if you were to integrate that expression in terms of Na, then you will end up getting an expression that looks like this. So essentially, the design expression for a batch reactor, so the amount of time it takes for a batch reactor to convert Na0 to NaF, that can be calculated using that expression. And then if you were to plot it, it should look something like this. So you'll see that the Na0 in the beginning of the reaction, when T is 0, your Na, this should be higher up, and B0, that should be 0, obviously, because you have no product in the beginning, right? And then as the time progresses, or as time goes to on the right, then your Na, or the amount of moles of your reactant, it should start to go down, and the number of moles of your product, which is B, it should then go up. So for this design expression basically just tells you that you are, then how long it will take for you to reduce the number of moles from Na0 to Na, or increase your number of moles of your product from 0 to Nb. So that's basically how you do it. And that's how you design a batch reactor. You calculate the time it will take. And this is done so for the first order reaction. You can even do it for a second order, third order, Of course, obviously, it gets more complicated the higher up you go. So therefore, you may have to use it. You may not be able to do it by hand, but then you can always use like mathematical, like MATLAB or anything else to help you solve these expressions. But that's essentially is that how you design a batch reactor, basically. Then we will jump into the continuously stirred reactor. And unlike a batch reactor, a continuously stirred reactor is a reactor that uses a continuous operation. As you'll see on the screen on the right, you have the inlet stream that is coming in. Then you have a mixer that is mixing your incoming feed with each other. And then you have the outlet stream that is taking the product out of the reactor. It's a continuous operation. That means that how much of the feed is coming in, the same amount is then going out in form of product. That means that the volume inside the reactor should always remain constant. That's actually one of the assumptions, but the volume is always assumed to be constant inside. And then you have a steady state operation when you're working with continuous CSTR. Why? Because there is no accumulation. So that means that everything is constant with respect to time. Nothing is changing with respect to time. That's what we mean by steady state operations. And just like a batch reactor, CSTR, they're also widely used in the industry. So for example, if you have homogeneous liquid phase reactions, petrochemical industry for catalytic reactions and polymerization process, continuous operations, continuous reactors are used, especially for environmental engineering. Actually, they use for wastewater treatment and biological reactions. Then again, they use a lot of continuous reactions. Pharmaceutical industry, they also use CSTRs or continuous processes for their active pharmaceutical ingredients, APIs for short. So, but basically, just like a batch reactor, a CSTR is using the exact same idea that you have a reaction taking place, but now you're just using you're just doing a continuous operation rather than a batch operation. So, but at the same time, just like earlier, there are also pros and cons when you're using a CSTR. The pro being that you have a steady state operation. A steady state operation tells you that nothing is changing with respect to time. So everything is the same throughout the time. The pressure, time profile, there's no accumulation basically in the system. And this allows for consistent product quality and allows you to have a more predictable process behavior compared to batch reactors. At the same time, the CSTRs, they have a higher productability as compared to a batch reactor, because you have a continuous flow of reactants and products through the reactor. And this allows you to have a much higher throughput and increased production efficiency compared to a batch process. The scalability in CSTR is much more, it's much more easier to scale or scale up a CSTR than it is for a batch reactor. Then you have a much more improved heat transfer in compared to a batch reactor, is because heat exchange can occur obviously continuously throughout the reactor, and this allows for better temperature control and reduces the risk of hotspots or thermal gradients within the reactor. It's like, imagine this way, that if you have water, or let's say water inside a batch reactor and it's staying there for 5 hours or 10 hours, then you would have heat spots, or heat would get accumulated someplace inside the reactor, right? But if you have a continuous operation and it comes back to the very first part that you have steady state conditions, so then the heat is always like getting exchanged with the new, because you have new feed coming in and the old product or the old flow just going out all the time. But that's also a pro within the CSDR. At the same time, it's much easier to automate operations in CSDR because it's basically essentially just in, react, and out, right? So therefore, it's much easier for you to have automated process control, which can regulate your flow systems, temperature, pressure, and concentrations. And it also kind of makes it a lot easier for you to be more consistent within the system. Because like I said earlier, for the batch reactors, you need one man to always keep a lookout for what is happening and what is not happening. Then you need to clean it up, remove it, and so on. You don't have that problem in CSDRs. So you can have a computer do all that stuff for you. But then there are a great deal of cons as well for a CSDR. The first one being that the control requirements can actually be slightly more complicated than a batch reactor. Like, sure, you can automate it, but then you would need to have very detailed or very almost perfect process conditions or process control systems, because now you have great deal of variables coming in, right? You have a flow coming in, so you have the flow rate, then you have inside the reactor, then you have a temperature and the pressure and the reactions and so on, and then you have a flow rate going out as well. So in order for you to be able to regulate everything at the same time in real-time conditions, it's very easy on paper, but in real life, it gets very complicated very quickly. And then there's also a great deal of limited flexibility in CSDRs in compared to a batch reactor. Is because, for example, like in the batch reactor, if you remember, I mentioned that it's very easy for you to change the scheduling, right? Like if today you only want to produce 100 liters instead of 50 and so on, but the same, it does not apply to a CSDR, and it's much less flexible. And also, if you would like to all of a sudden use the CSDR for a different product formation, like let's say today you don't want to produce methanol, but you want to produce something else, you actually can't. It's much more difficult in CSDR than it is in a batch reactor, because then you would actually have to change the conditions and even the process controls and the operating conditions, which actually also leads to downtime and product inefficiencies. Whereas in a batch reactor, it's basically just putting stuff in, and then you can always have a react as long as they are within the same process conditions. At the same time, then there's also something called a residence time. As you all may know, residence time is the amount of your feed or product that spends time inside the reactor. And the CSDRs, they exhibit broad residence time distributions, which can result in non-uniform reaction conditions and incomplete mixing within the reactor. Because the entire the fulcrum of CSDR, the assumption, which you'll see in a minute, is that we assume that everything that's coming in, it is being uniform mixed, and everything is reacting with each other, and only then will you then have the product going out. In real life, that may not exactly be true. And then at the same time, in a CSDR, you actually have a great deal of potential for having side reactions, because you are continuously introducing your reactants into the reactor, which can increase the potential for side reactions or byproducts that are being being created within the system. And finally, the equipment cost is also slightly higher than a batch reactor, because it actually comes back to the previous points, because you need to have a lot more control and a lot more specialized material to be able to produce or construct a CSDR in compared to a batch reactor. Like already using the first point, if you have already 5 additional variables, so you already have 5 additional process control equipment that you will not need in a batch reactor. That almost ends up increasing the construction cost for a CSDR in comparison to a batch reactor. And then once again, we have a few assumptions for an ideal CSDR, which we will keep in mind when we are deriving the design equation for a CSDR. Firstly, the same as before, we assume constant density. Assuming constant density is actually very important in CSTR as it is in comparison to a batch reactor, because you have a flow coming in into the reactor, it's mixing everything, and the product stream is going out. We are assuming that the volume inside the CSTR does not change. Actually, not assuming, it's one of the conditions that the volume inside the CSTR is not changing, right? We assume that the density is constant, which would then mean that the flow rate of the feed that is coming in will then be equal to the flow rate of the product going out. And that is actually a very important assumption that you have to keep in mind for a CSTR. And that assumption comes in by assuming that the density is constant throughout the CSTR. If the density was not the same, you have to remember that the mass is conserved. So the mass is the same, mass in, mass out, that's fine. But the volume tends to be slightly more complicated because the volume is dependent on the density. So if the density is not the same, then the mass flow rates might change a little bit in compared to the inlet and the outlet. So therefore, we assume that the density is the same. So therefore, we assume that the volumetric flow rate coming in is equal to the volumetric flow rate going out. That's the important one, but I'll mention that again when we are deriving the equation. The second one is that we assume uniform mixing. And that's also what I mentioned earlier, is that we assume that as soon as you add your reactants into a CSTR, they mix right away. And they are actually mixing uniformly throughout the reactor. And that's it's a very good assumption when you are deriving an equations, because it makes things very simple and oversimplify basically a lot of things. But in real life, obviously, that may not be the case. And when we say uniform mixing, then you should remember that earlier when we talked about the generation factor, then that assumption will then apply to a CSTR as well. Then we assume that it is isothermal, whereas the temperature remains constant. So we're not losing any heat or adding anything into the system. Then we assume steady state conditions for a CSTR. So that means that the flow rates of the reactants, they remain constant over time. And then obviously for today's webinar, we are going to have a look at homogeneous reactions. We're not going to have a look at heterogeneous. So for example, that means that if you have a CSTR, then it's basically a liquid-liquid reaction. Or like the same phase reaction, and therefore they are uniformly mixed. Then we are going to assume negligible change in pressure as well. That means that if you have a fluid that's coming in, and even if there is gas being produced, we don't assume that the pressure changes in any way. It again simplifies our mass transfer and reactor sizing if you're working with it. And once again, just like previously, we are assuming constant reaction rate, which is kind of linked up with the uniform mixing. And the last one, instantaneous mixing, that's what I mentioned earlier, actually, is that the fact that as soon as you add something, it gets mixed up right away. But there is no delay, or there's no delay between the introduction of the reactants and the uniform mixing. So these are the main assumptions that we will keep in mind when we are designing it. So now coming down to the designing of a continuous stirred reactor. So we will start off with, again, the mole balance. You have in minus out plus generation is equal to accumulation. It looks something like this. But in this scenario, now since we have a feed coming in, so we do have Fj0, we have a feed going out, so that would be Fj. The integral generation, yes, we have generation because we are having a chemical reaction. But since we assumed steady state, that will mean that our last term, accumulation term, that will be 0. There is nothing being accumulated inside the reactor, but rather we have coming in, it generates, and it goes out. Nothing is being stored inside the reactor, unlike a batch reactor. So the accumulation factor will then be 0. And then if I was to rearrange this expression for V, volume, then you end up getting an expression that looks something like this. And which is basically the inlet flow minus the outlet flow divided by the rate of expression for that component. And that normally is for our reactant. So J would be our component that we have a reactant that is coming in. And then the important thing that you might have to remember, that the molar flow rate, which is the capital F, it can be rewritten in this form as well, in terms of concentration and the volumetric flow rate. So that means that the molar flow rate, the F, is equal to the concentration multiplied by the volumetric flow rate. So C times small v. Small v, that's the velocity or the volumetric flow rate. Capital V, that's the volume. But just keep that in mind. So therefore, we can then rewrite the expression that we derived earlier for CSTR in terms of this expression that you see on the screen now. So V is equal to the concentration times by the inlet concentration times by the inlet flow rate minus the concentration times by the volumetric flow rate of going out, divided by the rate expression, of course. So that's just another expression that you can always use, and that is the expression that we will then use when we are designing a CSTR. And in this expression, which is written down, just want to point out that even though I wrote V0 in the first and then V in the second, because when you write the expression, you don't obviously assume constant density or same volumetric flow rate when you're designing an expression. But if you were to implement the assumption, then V0 is equal to V. They're the same. So you will end up getting the same velocity, volumetric flow rate, basically. But then, just like earlier, if we were to look at an expression that is a first order reaction where A gets converted into B, then you can write the rate expression like the one right here. And then, but in this scenario, earlier we wrote the concentration in terms of moles divided by volume. In this scenario, we are actually going to write it as molar flow rate divided by the volumetric flow rate. So capital F divided by V. So that means that when you are designing the CSTR, then you need to write the rate expression in terms of the molar flow, and the volumetric flow rate. And then we go back to the expression that we had before. Then you insert the rate expression for minus RA. Then you get that one. And then if you were to rewrite it, then you end up getting an expression that looks somewhat like this. And then you can rewrite it even further in order for you to get an expression that looks something like this. So the design expression for a CSTR is then the velocity divided by the rate constant multiplied by your inlet flow rate divided by the end mole rate minus 1. So what this expression is telling you is the volume it will be required for you to reduce the molar flow rate of A from FA0 to FA. So what you would like to achieve is that you would like to reduce the flow rate from this value to that value, and then how much volume it will then take you in order for you to achieve that conversion. But that's essentially what you do. And then just like earlier, you can even write the same for second order, third order. It just gets more complicated, but then you will need a numerical or a computer program to solve it for you. But that's essentially how you then design a CSTR system. But then coming down to the third type, which is a plug flow reactor. And a plug flow reactor is somewhat slightly more technical than compared to the previous two reactors, because in a plug flow reactor it's not a reactor tank or something, but you are now assuming that it is a continuous flow process, but you're imagining as if you have a cylindrical pipe and you have a flow coming in and it's reacting within that pipe. And that's what we call a plug flow reactor. And the plug flow reactors, they are, typically used or modeled for gas phase reactions. And what happens is that, I want you to imagine that you have a very long cylindrical pipe, right? So you have a flow coming in, it reacts, and then it goes out on the other end. Now, but the important thing in a plug flow is that um, your components, like for example, let's say your component A, it will be very highly concentrated in the entrance in comparison to what it will be in the end, right? So in the very first part, you would have very high conversion, but then as you move through the cylindrical pipe, your conversion then should start to reduce slightly. Why? Because then you have a much smaller amount of those reactions. And therefore, so that's essentially what a plug flow reactor is. And then there are also a great deal of assumptions when we are working with a PFR, and that is something that we'll look at into a minute. And then the PFR is also used in a great deal of different industries. It's mostly used in the petrochemical industry, in the catalytic reactions, hydrogenation processes, and olefin polymerization. Once again, under environmental engineering for, in wastewater treatment, specifically for oxidation processes or disinfection processes. At the same time, it's also being used in the food and the beverage industry for continuous fermentation, enzymatic reactions, and sterilization. And normally, when you're working with a PFR, it makes more sense to have like a catalyst. When you're using catalyst, for example, that's when, typically a lot of people, they tend to use the plug flow reactors. So just like the previous reactors, there are a great deal of pros and cons when you're working with a PFR as well. The first pro being that you have a very efficient heat transfer in a plug flow reactor, because the reactants flow through the reactor in a continuous plug-like manner, and therefore it minimizes the radial temperature gradients. At the same time, you have a very uniform residence time inside a plug flow reactor. It's just because the nature of the reactor ensures that all the reactants, they spend the same amount of time in the reactor, which leads to a uniform residence time distribution, because you have a continuous flow coming in, and then if the cylindrical pipe is, let's say, cylindrical size is 50 meters, then all of your particles, they will end up spending the same amount of time throughout the pipe, inside the reactor, and therefore the residence time will be constant, which is slightly different from a CSTR. And the PFRs, they often achieve higher concentrations compared to reactors with mixed flow patterns, because reactants are exposed to optimal reaction. And thirdly, you have a higher conversion in PFR. It's because in compared to the reactors with mixed flow patterns, because reactants are exposed to optimal reaction conditions for a longer duration, and hence you end up getting a higher conversion. And then it's also very easy to scale up a PFR when compared to a batch reactor, because scaling up involves replicating the reactor design and increasing flow rates while maintaining the similar operating conditions. And then finally, the PFR operates continuously, which allows for steady state operation and continuous production of products. This leads to a higher productivity, reduced downtime, and improved process efficiency compared to the batch reactors. And now coming down to the cons of a PFR, the first one being that achieving a perfect plug flow in practice is challenging, and deviations from the ideal plug flow behavior may occur due to uneven flow distribution. And also there could be possible back mixing. At the same time, then there is also limited. PFR is less flexible than batch reactors in terms of production scheduling and product variability. And obviously, because it kind of matches up with the CSTR, because if you would like to all of a sudden use the PFR for a different product, then that's not as easy as the scenario with a batch reactor. And also maintaining optimal operating conditions in PFR requires very complex control strategies to regulate the flow rates, temperature, and reactants, and just like we talked about for the CSTR. And also it is integrating heat exchangers into PFR designs can be quite challenging, especially with high heat release rates or highly exothermic reactions. And therefore, if you would like to add heat transfer while maintaining plug flow behavior, it gets very complicated very quickly. And also in practice, PFR may experience challenging or bypassing of reactants, which leads to uneven distribution and reduced reaction efficiency, which is not a case that we see in batch reactors. And then coming down to the assumptions that we may have for the PFR, the first one being that we assume a perfect plug flow. That means that they will go through the plug, go through the flow is the primary assumption, of course, is, and that's where it gets the name from, is that you assume the perfect plug flow. That means that each volume element of fluid moves through the reactor without mixing with the adjacent element. And that's what we call the axial flow. And then we assume that there's a constant flow rate. That means that all the particles, all the mass, they are constant throughout the PFR. And then it kind of matches up with the first one, and we assume that there is no axial dispersion within the PFR. That means that there is no mixing between among the particles in the length. Like for example, you would assume that the like imagine a cylindrical pipe, and the reactors that are at the very top, they don't react or mix with the reactor components right below or the below. So that's what we possibly mean. Yeah. And then we obviously assume a uniform temperature profile. That means that the temperature is constant throughout the PFR. And once again, we use the isothermal condition just like did before, and the ideal gas behavior and constant reaction rate, just like the same assumptions that we used earlier. So the only additional assumptions that we use for PFR, that is actually in terms of the flow rate, the plug flow, and in terms of the axial dispersion. But then coming down to the designing of the PFR, if you would like to design a PFR, or when we are deriving the expression, then you have to assume, or you have to imagine, that we take a cylinder that looks a pipe that looks something like this, and then imagine a instantly small amount of volume area in which the reaction rate is completely constant. And that's what the V and the V plus delta V comes in from. So this very small area called delta V, that's the area where the generation factor is entirely constant. And we will use that in order to design or derive an expression for PFR. So we go down, and then you once again start off with the very basic mole balance, and you rewrite the one that we derived earlier, and you but now using the diagram that I just showed you, you are starting off with a mole flow in the beginning of V. That's what the V means, and then minus the molar flow rate at V plus delta V. So if I can actually go back, you see that we have the cylindrical pipe, we have a very small, infinitely small amount of volume change, and that is V, and then V plus delta V. And that's what we are writing the mole balance for. And now, since we are assuming that the rate of reaction within that area is constant, that means that, and everything else is constant, that means that the temperature, pressure, and so on and so on, that means that the generation factor can then once again be rewritten like the one that we showed earlier. And of course, since we are working with steady state, that means that the accumulation is equal to 0. And then we will rewrite that expression in terms of that expression. Now, if you remember from your calculus classes, this one looks something very similar to the first principle of the differentiations. So by doing so, then we can rewrite this expression as, in terms of R of the rate, is equal to the delta molar flow rate divided by the change in volume. So now we end up getting a differential equation. So now, but for you to use this expression, Rj is equal to dF divided by dV, what we want the volume. So then we will rearrange this expression. So we take the V to the other side, and then we will integrate this expression. And we will integrate in terms of the molar flow rate, because and then of course you can integrate this expression and you end up getting the solution, which we'll also do in a minute. But this is the actual design expression, the integral design expression for a PFR reactor, or sorry, a PFR. There we go. And then essentially what you're saying by this expression is that you would like to find the volume for which you are integrating from the inlet molar flow rate of your reactant towards the final molar flow rate of the decided component. But then we will once again take a simple first order reaction that looks like A to B, and then we will rewrite that expression in terms of the rate, and the Ra is equal to minus K, and then we will once again rewrite the concentration in terms of the molar flow rate divided by the volumetric flow rate. And then using the integral, just like before, you insert the expression that we just wrote at the top. And if you integrate, I'm not going to go into much detail how to integrate it, because I would assume that you already know how to do that. But if you were to do it, then you will end up getting an expression that looks somewhat like this. So something very similar to the CSTR, the one that we saw earlier. But unlike the CSTR one, we didn't have the LM, but it's actually similar to the batch, but not the CSTR. There we go. But this is the design expression for the PFR reactor. And this essentially was telling you is that if you would like to convert the the volume that you need of a PFR to convert your volumetric flow rate of A from FA0 up until FAF, the final molar flow rate. There you go. So that's essentially how you normally design, or those are the, so essentially that is the introduction to the reactor types and their design equations, and normally how you would, design them using the assumptions that you might have to take. But then you have to remember that there are a great deal of key factors that you have to keep in mind that are also very important when you are designing a reactor. They don't necessarily have a direct impact on the reactor type, but rather they're quite the opposite. So depending on what sort of conditions you have, or what sort of factors you have, that greatly impacts what sort of reactor you can and cannot use. So that's what we look at right now. The very first factor that you possibly could have is a catalyst. Now, a catalyst, if you don't know it already, it increases the rate of a chemical reaction without itself becoming permanently changed by the reaction. And then what a catalyst basically does is that it increases the reaction rate, which allows you to run the exact same reaction in a smaller reactor, right? And even at times, if you remember, that it reduces the activation energy, hence you can then also perform the same reaction at a lower temperature. Now, what it does in terms of a reactor design is that if you are using a catalyst, firstly, you will need a much smaller reactor, and if possibly, you can use a lower temperature. That means that your equipment size, cost, and your utility cost, they can easily be reduced. So that's one of the key factors that you have to keep in mind, that if you have a reaction that can be catalyzed by a specific catalyst, it has a great impact on your reactor design, because it can reduce the cost and the operating cost of your process. But it does not really come without another price, because it can also have a great deal of constraints onto the reactor, especially for the operating conditions. Because firstly, for example, the catalyst, if you use a catalyst into a reactor, then it needs to be able to work for a reasonable length of time between but the thing is that it doesn't really come without a price, because if you do choose to use a catalyst within a reactor, then the conditions of the reactor, inside the reactor, let's say the operating conditions of the reactor, should ensure that the catalyst activity is available for a reasonable length of time. So for example, let's say that you're using a catalyst and the catalyst can only work at a temperature of 200 degrees Celsius. But now all of a sudden you just increase the temperature of your reactor to 300 degrees Celsius, then that catalyst is completely useless to your reactor, right? So therefore you always have to find the mix and the balance between the reactor operating conditions and the catalyst that you may end up using. At the same time, you have to remember that catalysts, they are very unstable at higher temperatures. So therefore, if you have a reactor that is being operated at 300 degrees Celsius, and then you would like to use a catalyst all of a sudden, then you might have to reduce the temperature of your reactor in order to facilitate the catalyst. And that obviously may have an effect on your yield, on your selectivity of your reactants and the product, and so on. So therefore, it's kind of like a very mix and a compromise of sorts between the two conditions. And finally, catalysts are very prone to contaminants. So if you have a feed that is coming in and it has different contaminants, then they could have a negative impact on your catalyst going forward. So that could actually end up increasing the operating cost in compared to if you were not using a catalyst. If you always have to go in and clean up the catalyst, or if the catalyst kind of all of a sudden stops working in the system. So therefore that these are always the considerations that you have to keep in mind. And then the second one, the biggest consideration that you have to keep in mind, that is the temperature of your reactor. Because a higher temperature will always increase the rate of reaction, the rate of diffusion, and the mass transfer, which is great. But if your reaction is endothermic, right, then it's great, because if you increase the temperature, the equilibrium constant will be towards the product side. But if your reaction is exothermic, then you can't increase the temperature of your reactor, because by doing so, the equilibrium constant will then start to move towards the reactant side. But rather, for exothermic reactions, you will have to reduce your temperature. By doing so, then you risk reducing the rate of reaction, or the rate of diffusion, and the rate of mass transfer rates. But most of the times, you'll see that by experimental data, you'll see that the higher the temperature, the better it is for your reactor operating conditions, unless you are faced with different constraints in the system. So imagine that you have a reactor in which you have biological agents like cells, enzymes, microorganisms. Then you have to remember that majority of these living organisms, they cannot survive at higher temperatures. So when you're designing the reactor, then you have to check and ask if it includes any microorganisms, or if it is just basic methanol and water and so on. Normally, microorganisms, they operate between 20 to 50 degrees Celsius. That means that at relatively medium temperature. But if you're going very low in your reactor, then you risk them becoming denatured and become deactivated. So therefore, it's kind of like a very mix that you have to select what temperature will be the most optimal for your reactor, and also for the content within the reactor. At the same time, the same applies to organic compounds, because if you increase the temperature, assuming that it will increase the rate of reaction, the organic compounds, they undergo thermal degradation within the system. At the same time, if you actually have gases such as oxygen and nitrogen in your reactor, then the thermal degradation is a lot faster. So therefore, it's always a good idea to have the temperature at an optimal level if you have organic compounds present in the system. At the same time, at higher temperatures, it is very difficult. It is more difficult to suppress side reactions such as polymerization or auto-oxidation, and these could end up having a negative impact on the safety and, of course, the selectivity of your reactants. And it's also because the selectivity of the oxidation reactions also decreases as the temperature goes up. And it's because it becomes harder to maintain the locally optimal concentration of feed, oxidant, and product, and therefore the system then has a tendency to oxidize the product. So that's also one of the conditions. And also, if your reaction is exothermic, and if you are all of a sudden increasing the temperature, then it will be very easy for the system to simply go out of control. You don't really want to have, in an exothermic scenario, like I said earlier, that you don't really want to increase the temperature, because otherwise then it will be very difficult for you to reduce the temperature to the optimal conditions. And also, finally, the biggest one, that tends to be that there is a great deal of construction limitation when you're working with higher temperatures. When it comes to steel or the alloys, you will always see that from the construction partner, there will always be a limitation on how high the temperature the reactors can handle. So, for example, the allowable stress for steel, it starts to decrease significantly if the temperature is above 300 degrees Celsius. At the same time, the pressure vessel design code is the limit for that is also given to be the pressure vessel design code limit the maximum temperature at which the alloys can also be used. So you always have to keep that in mind, that if you have a very high pressure inside the reactor, then you don't really want to increase the temperature either, because that could be much more dangerous to your employers and engineers and the operators. So therefore, when you are designing the reactor, the temperature of the reactor plays a very important role on how you should design it and how you can design it. And the third factor that comes in, that is the pressure of the reactor. Of course, the pressure of the reactor is dependent on the phase of the reactor. If you only have gas-to-gas reaction, then increasing the pressure tend to increase the reactant activity and increase the reaction rate. The more the pressure, the more it's interacting, and more the reaction rate. But then there are two scenarios that you can possibly have inside the reactor. The first one being that if the reaction is increasing to the increase of the total number of moles, and then if you increase the temperature, then you would get the negative impact. But rather, you should decrease the pressure so that the pressure should increase of its own. At the same time, if the reaction is leading to a reduction to the total number of moles, then the equilibrium constant will only be moved towards the towards the product side if you increase the pressure. So you always have to keep that in mind as well. Working with the gas to liquid reactions, then the higher pressure that you have, it will allow for a higher gas solubility, which will then also increase the reaction rate and so on. So therefore, so the pressure is also a very important factor when you are designing your reactors. And finally, you of course have the reaction phase. Are you working with fluids? Are you working with gases? Are you working with solids? If you're working with gases, for example, it doesn't really make sense for you to use a CSTR, right? If you're working with fluids, then yes, it makes sense to use a CSTR. But if it's only gas, if it's gas and liquid, then once again, it makes sense to use a CSTR. If you're working with solids, then again, it's still a limitation for you to use a batch reactor. So therefore, there's all great little considerations about if you're working with what sort of phase that you are working with. Fluids are very easy to work with because they're very easy to handle, compress, meter, heat, and cool in comparison to gases, for example. And if you have solid reactants and products such as cells or polymers, then they are mostly suspended in a gas or liquid for reaction. You can't just throw solids inside a reactor and expect them to react. But therefore, then you will have to make a decision about what sort of inert solvent that you must be using. So there are, again, a great deal of considerations that might have to come in handy there. But I might add that these considerations, they're not necessarily made by engineers. It's actually somewhat of the considerations that you might have to go and ask different chemists, because they are the ones that are working with day-to-day operations of these, or day-to-day research of these reactions. So it might not be the area of a chemical engineer to go in and decide about what temperature is optimal for a reaction, but when it comes to the reactor design part of it all, then your chemical engineering skills come in play, because then you have to make a balance between that, okay, so the reactor is, I have a reactor that is a CSTR reactor. It needs to be operating at 200 degrees Celsius or 150 degrees Celsius. The catalyst can only work at 180 degrees Celsius. That means that the optimal temperature that we can use maximum is 185. Then you do a simulations, then you do the optimization, and then you decide if it should be like what sort of process control you should be applying to it, what sort of volume it should have, what sort of the assumptions that you should be working with. So that's where the engineering comes into play. But all these, like the reaction rate, the experimental data, the what temperature works best, that's not something that is expected of chemical engineers per se, but that's rather more of the expertise of chemists when they're working at a pilot scale, or when they're trying to come up with the recipes for different products. And finally, so summarize everything that we've looked at today in this webinar, the general procedure for reactor design then ends up looking somewhat like this. So imagine that you have been tasked to design a reactor. Then the very first thing you should do is that you collect the required data, and that would have to be experimental data. So for example, A plus B is equal to C. How much selectivity does it have? How much the yield does it have? How much is the reaction rate? How much is the stoichiometric coefficients? All that stuff that comes from experimental data. That's not something that you can figure out on your own by looking at a piece of paper. You do that, then you, of course, you select the reaction conditions that would optimize the conversion and the yield. And that's what we looked at right now. So that would be the temperature, the pressure. If you have solids, what sort of inert solvent you should be using, what sort of reactant phase you should be using. Should it be a gas liquid phases, or should it be liquid phases, and so on. And then you start to look at the material of construction. And that's what I talked about earlier, that if you're working with a very high temperature, then obviously you need to look at very specific alloys. If you're looking at very specific pressure ranges, then you need to go out there and check which sort of steel or alloy can be used. At the same time, it also affects on what sort of chemicals you will actually be using inside the reactor. Let's say you have sulfuric acid inside the reactor. Then again, you can't really use specific steels for it. You have to use specific alloys for it. And that's where your equipment costs and equipment cost comes in. If you were to find out that the material of construction is too expensive, let's say all of a sudden you wanted a batch reactor that should be able to hold 5,000 liters of sulfuric acid, and now you want a very specific type of metal, and that costs too much. Then you go back to the chemist and you tell them that it doesn't work out, it's too much cost. What else can we do, or what sort of other what do you call it, the reaction conditions can be changed, or if you can break it down into something else, or and whatnot. But if the cost is reasonable, then you start to determine the rate limiting step of the reactions, because of course, if you have like A plus B plus C, and you have multiple reactions taking place, just like we see in chemical reaction engineering, you need to be able to figure out the rate limiting step, and that which is also done so by using the experimental data. If not experimental data, you can also do it theoretically, but it's just majority of the time it's done so by using experimental setup. Once you have that in place, once you have decided on the rate limiting step, Then you finally start working at the sizing of the reactor using the design equations and equipment costing. That's where you make a decision about whether it should be the batch, CSTR, PFR. The three of these, then you decide that it makes sense for us to do a CSTR. Then you use a design equation, which we looked at today. You put in all of your variables, you put in all of your equations, you calculate it, you do the modeling, and then you figure out how much of a volume you need. And when you have the volume, you can then finally start incorporating the equipment cost for it. But you must remember that when you design a batch reactor, for example, using the design equation, and you get the volume to be 1,000 liter. Oh, no, sorry. For a CSTR, the volume comes out to be 1,000 liter, for example, right? You have to remember that if you decide to use catalysts, if you decide to use some other equipment, if all of a sudden you would also like to use a heat exchanger, the volume that you get from the design equation is only for the reactants and the products going in. So in order for you to incorporate the catalysts, the heat exchangers, all the other piping and process equipment, then that volume should of course be slightly bigger than the one that you calculate using the design equation. It's just a very small, minor consideration that you might have to do when you are designing it, because just keep in mind that when you're using the design equations, they are based entirely on assumptions, and you're not essentially taking into account the catalyst volume or the heat exchanger volume or the process control equipment and so on and so on. But then once you have all that in place, then you start estimating the performance using a pilot plant, or once again using experimental data. And once you have the data in place, then you can start optimizing the performance, going back to step 2, and then rerunning your reactor and the performance and optimizing it as much as you can. Once everything is set to place, only then can go ahead and scale up your reactor from a pilot scale to a bigger industrial production scale level. But that's essentially how you normally design a heat exchanger. Oh, sorry, when you normally design a reactor in a procedure for a production facility. Great, and that was actually all that we had for today for this webinar. And I really hope that you found the information to be helpful and something that you can use in your everyday life as a chemical engineer, whether in school or in the industry. And if you would like to learn more about reactor design or any of the other chemical engineering topics, then you should check out our other upcoming webinars and online courses at www.ChemEnggLife.com, because we do have a lot more webinars coming up where we look at much more details of reactor design, specifically in the batch, CSTR, and the PFR, and what would happen if you take the heat transfer into account, and how would you like to, and how would you design it for specific scenarios and for specific problems that you might encounter in the industry. So do stay tuned for our other webinars. And like I said, we also have a lot of online courses where we go into, once again, much more detail in these reactor designs. So, but having said that, I thank you all very much for signing up, for joining, and for listening to the webinar. And I really hope, once again, it was helpful. And we'll be looking forward to seeing you once again in our future webinars. Great. Thank you, and have a great day. Thank you.